From the moment we are born, gravity is our unseen companion. It presses our bodies into the ground, dictates the weight of every object we lift, and pulls the rain from the clouds to the soil below. When we leap into the air, it calls us back. When we stumble, it is gravity that hastens our fall. It is so ever-present, so woven into every heartbeat of our daily experience, that we almost never question it. Children drop toys from high chairs and learn its lesson long before they can spell the word itself. We take gravity as obvious, as simple as one of the few things in the universe that does not need explanation. Yet this most familiar of forces is also the most mysterious. In school, we are taught about 4 forces of nature. The electromagnetic force governs light, electricity, and magnetism. The strong nuclear force binds quarks together into protons and neutrons and holds atomic nuclei together with unimaginable strength. The weak nuclear force, despite its name, drives the transmutations of particles, shaping the nuclear reactions that light the stars. These 3 forces together form the proud edifice of the Standard Model of particle physics, a framework that has been tested to exquisite precision and rarely fails. They are carried by exchange particles, the photon for electromagnetism, the gluons for the strong force, the W and Z bosons for the weak force. These particles mediate their interactions through the quantum fields that pervade the vacuum, but gravity does not fit neatly into this particle picture. We do not have a confirmed particle that carries it. Theories predict a massless spin-2 particle called the graviton, yet despite decades of searching and theorizing, no such entity has been detected. The Standard Model, the crown jewel of 20th century physics, makes no place for gravity at all. General relativity, Einstein's masterwork, describes it instead as geometry, as the curvature of space-time itself, and so gravity stands apart, the familiar stranger, the only one of nature's forces that resists being brought into the same family portrait. The differences run deep. Electromagnetism can be shielded. We can block light with a curtain, bend radio signals with walls of steel. The strong and weak forces act only at subatomic distances, vanishing beyond the scale of the nucleus. But gravity cannot be blocked, cannot be shielded, cannot be tuned down. Every atom in the cosmos attracts every other atom with a force that extends across infinite distance. The pull may grow weaker with separation, but it never vanishes. Its reach is universal. And though it is the weakest of the known forces, its range ensures it shapes the grandest structures of the universe. It sculpts galaxies, dictates the fates of stars, and binds planets to their suns. What the strong force is for the nucleus, gravity is for the cosmos. And yet, in human life, it is gravity that feels strongest. A tiny magnet can lift a paperclip against the entire pull of Earth's mass. That small act demonstrates how feeble gravity truly is compared to the electromagnetic force. To overcome the attraction of a whole planet, you need only a refrigerator magnet worth a few cents. But because we live surrounded by enormous masses, from mountains to planets to stars, gravity overwhelms our senses. The universe has a way of hiding its deepest truths behind familiarity. This tension between everyday experience and theoretical difficulty is what makes gravity so fascinating. We can calculate its effects with remarkable precision. Newton's law of universal gravitation gave us the motions of the planets and the trajectories of comets. Einstein's general relativity explained the bending of light by stars, the expansion of the cosmos, and the existence of black holes. But even with these triumphs, we cannot yet say with certainty what gravity truly is. We cannot decide whether it belongs with the fundamental forces of particle physics, or whether it is something altogether different, perhaps not a fundamental force at all, but a mirage created by deeper laws still hidden from view. It is worth pausing here to reflect on the very idea of a fundamental force. When physicists say a force is fundamental, they mean it cannot be explained as arising from anything else. It is a bedrock, a basic interaction from which higher-order behaviors emerge. Electromagnetism is fundamental in this sense, and from it arise chemistry, biology, and the technologies that define civilization. But if gravity is emergent, then it is not a bedrock, but a pattern, a consequence of something more elementary. It would be like heat, which is not a fundamental entity, but the collective jostling of molecules. Or like pressure, which is nothing more than the average force of countless atomic collisions. To question whether gravity is fundamental is not to diminish its importance. It is instead to place it under sharper scrutiny, to recognize that nature may be playing a subtler game than our first impressions suggest. What we call gravity may be the tip of a deeper iceberg, a surface appearance of hidden structures. And that possibility carries profound consequences, not only for physics, but for our very understanding of reality. If gravity is not fundamental, then our picture of the universe must be rebuilt from the ground up. Space and time themselves may not be the immutable stage we thought they were, but emergent phenomena woven from quantum information or entanglement. In that vision, the familiar pull we feel when we drop a stone or leap into the air would not be an ancient force etched into the fabric of nature, but the whisper of something more abstract, more elusive, and more fundamental than space-time itself. But before we follow that thread into speculation, we must first confront gravity, as Einstein taught us to see it. To understand why it refuses to join the standard model, and why so many suspect it may not be fundamental, we need to revisit the vision that reshaped our understanding of space and time. For if Newton gave us gravity as a force acting across distance, Einstein gave us gravity as the curvature of space-time itself, a picture so radical that it forever changed our understanding of the cosmos. And that is where we must turn next. Gravity has always been with us, but our understanding of it has shifted many times across history. For the ancients, it was the natural tendency of heavy things to fall toward the earth, a kind of built-in directionality in matter itself. For Newton, it became a universal law, an invisible attraction acting between every mass in the cosmos. For Einstein, it transformed again into the curvature of space-time, the shape of the very arena in which events unfold. Each step seemed final, yet each was later revealed as incomplete. This pattern should already make us cautious. Perhaps the version we hold today, as elegant as it is not the last word either. When we say gravity is different from the other forces, it is not only a matter of strength or range. The others live comfortably inside the quantum framework, where interactions are mediated by discrete quanta. Photons carry the electromagnetic force. Gluons carry the strong force. W and Z bosons carry the weak force. These carriers can be produced, studied, exchanged in particle collisions. But gravity has resisted every attempt at quantization. The hypothetical graviton remains undetected, not only because its effects are minuscule, but because the very mathematics of gravity resists the simple machinery that works for the other forces. This unease shows itself in the deepest puzzles of modern physics. Black holes, those regions of extreme gravity, confront us with paradoxes about information and the fate of quantum states. The singularities predicted by general relativity signal breakdowns where the equations lose all predictive power. At the same time, the expansion of the universe, driven by dark energy, forces us to consider whether gravity, as we understand it, is even complete. The other forces may leave mysteries about unification, but only gravity forces us to question whether we are even asking the right questions. Yet to the human mind, gravity feels fundamental because it is immediate. A dropped stone, a falling apple, a leap into the air and back to the ground, all give the impression of inevitability. Our very sense of up and down is defined by it. It anchors our balance, shapes our architecture, determines our landscapes. No wonder it became the first force to be codified into a universal law. But familiarity should not be mistaken for fundamentality. Heat feels fundamental too, until we learn it is the jostling of atoms. Sound feels fundamental, until we learn it is the motion of air. Perhaps gravity belongs in this category, a phenomenon that feels primary only because we are immersed in it. This possibility is more than philosophical musing. Already we have examples of emergent phenomena that mimic forces. Consider the way pressure arises from billions of impacts of molecules. Pressure is not a separate law of nature. It is the collective result of deeper rules. If gravity could be explained in a similar way, it would cease to be a fundamental law and instead become a large-scale behavior, the visible consequence of something unseen. Still, The majority of working physicists continue to treat gravity as a fundamental interaction, not out of blind adherence, but because the evidence we possess so far fits that description. Einstein's field equations describe planetary orbits, gravitational lensing, the timing of pulsars, and the waves detected rippling through space-time. These are not illusions. They are real phenomena with measurable effects. The question is whether they are the direct outcome of a fundamental force or the emergent echo of something more hidden. The Standard Model of particle physics stands as one of the most successful scientific constructions of all time. Its predictions have been verified again and again in particle colliders, from the behavior of quarks and leptons to the discovery of the Higgs boson. Its precision is breathtaking, and yet it has a glaring hole. Gravity is absent. We cannot describe the cosmos fully without it, but we cannot fit it into the framework we trust most. This contradiction is not sustainable. Something has to give, and many suspect it will be our assumption that gravity is fundamental. If that suspicion proves true, then the consequences will ripple far beyond physics journals. It will mean that the fabric of reality, as we imagine it, is woven from something deeper than space-time itself. It will mean that what we experience as attraction between masses is not a basic property of the universe, but a grand illusion, a secondary effect of more primary structures. To grasp that idea, to even glimpse what it might mean, requires that we understand the revolution Einstein brought. Only then can we see where it falters, and where new visions may arise. And so, as we leave behind the comfort of gravity as a force among forces, we turn toward Einstein's radical reimagining, where mass and energy bend the very geometry of existence, and where matter and space-time engage in a cosmic dialogue. This is the vision we must confront before we can ask whether gravity is truly fundamental, or whether it is a familiar stranger hiding a deeper truth. Gravity's story is not just about equations and theories. It is about the way it has shaped our imagination of the universe. For millennia, people watched the skies and wondered why the moon did not fall, why the planets wandered among the stars, why tides rose and fell with uncanny rhythm. When Newton revealed that the same force that pulls an apple down also keeps the moon in its orbit, it was a moment of unification that changed humanity's place in the cosmos. The heavens and the earth were no longer separate realms. They were bound by the same invisible law. It was a breathtaking insight, and for centuries it stood unchallenged. Gravity seemed not only fundamental but eternal, but with every advance came cracks in the picture. Mercury's orbit shifted in ways Newtonian gravity could not explain. Starlight bent as it passed the sun, something Newton's equations could not predict. These cracks were not dismissed. They were measured, tested, puzzled over, until Einstein's general relativity offered a new lens. Suddenly, gravity was no longer a force transmitted across space, but the shape of space itself. What Newton saw as action at a distance became the natural motion of matter along curved paths. The apple fell not because of a pull, but because it followed the curve of space-time. This was more than a new theory. It was a revolution in perspective. It revealed that space and time are not passive arenas, but active participants in the drama of existence. Planets orbit not because of invisible tethers, but because space-time itself guides their paths. Mass tells space how to curve, and space tells mass how to move. With this picture, Einstein explained Mercury's orbit, the bending of starlight, the slowing of time near massive bodies. His equations opened the door to black holes and to the expanding universe. Gravity had become geometry, and our understanding of reality would never be the same. Yet even in Einstein's vision there is unease. Geometry is a language of smoothness and continuity. Quantum theory is a language of discreteness and probability. The two languages clash when we try to apply them together. In the heart of a black hole, or in the first instant of the Big Bang, relativity predicts infinities where it should not. Quantum mechanics predicts fluctuations that relativity cannot accommodate. Each is brilliant in its own domain, yet the two together refuse to harmonize. Gravity, in Einstein's hands, solved mysteries that Newton could not, but it created new ones that still haunt us. This dissonance is why many physicists suspect gravity may not be fundamental. The other forces fit inside the quantum picture, even if imperfectly. Gravity resists it. Perhaps it resists because it is not meant to be forced into that framework. Perhaps gravity is not a missing piece of the puzzle, but the image that emerges when the puzzle is complete. If so, searching for gravitons might be as misguided as searching for atoms of heat. We may be mistaking an emergent property for a fundamental one. Such thoughts are bold, even unsettling. They challenge centuries of intuition, yet they are also natural in the history of science. Time and again, what we thought was basic has turned out to be derivative. The solidity of matter dissolves into quantum fields. The permanence of time dissolves into relativity. Why should gravity be any different? Why should it be exempt from the possibility of emergence? Still, even if gravity is emergent, it rules our world. We cannot live without it. It shapes our biology, dictates our technology, and frames our aspirations. To escape Earth requires speeds of 11 km per second. To orbit requires delicate balances of velocity and altitude. To land on the moon required humanity to master its subtleties with exquisite precision. Gravity may be the weakest force, but it demands our respect. It is the sculptor of landscapes, the choreographer of planetary dances, the silent conductor of cosmic evolution. We find ourselves in a paradox. Gravity feels both familiar and alien. It is the first force we learn about, and the last one we understand. It is universal yet elusive, weak yet dominant, classical yet resistant to quantum description. It is the stranger we think we know, and to truly see why it may not be fundamental, we must step into Einstein's vision in detail, to walk through the geometry of space-time, and witness how it reshapes our understanding of attraction, mass, and motion. Only by appreciating the depth of that revolution can we begin to glimpse where it falters, and why some now argue that gravity is not a bedrock of reality, but the shimmering surface of something deeper. And so, as this first chapter closes, we stand at the threshold. We have seen gravity contrasted with the other forces, noted its absence from the standard model, and sensed the unease that surrounds it. Ahead lies Einstein's world of curved space-time, where geometry replaces force, and where our familiar stranger takes on a new and astonishing form. To understand why gravity may not be fundamental, we must first see how it bends the very stage of the universe. That is the journey we now begin. When Albert Einstein unveiled his general theory of relativity in 1915, the world did not immediately grasp its meaning. The mathematics was intricate, the implications radical, and yet beneath it lay a simple but staggering idea. Gravity was not a force pulling at a distance, as Newton had described. It was the bending of space-time itself. Matter and energy did not just move within the stage of space and time, they sculpted that stage, curving its geometry, altering its flow. And objects did not need to be pulled across emptiness. They simply followed the natural lines of that curved geometry. With a few strokes of insight, Einstein transformed our understanding of the cosmos. Imagine space-time as a fabric, though not a fabric made of threads, but one of geometry itself. Place a planet upon this fabric, and it dips, creating a curve. A passing comet, moving nearby, follows that curve, not because the planet reaches out with invisible strings, but because the path itself has changed. What feels like a gravitational pull is in truth the geometry of space-time guiding the comet's motion. The apple that falls to Earth is not tugged downward by a mysterious force. It is tracing the straightest possible line through curved space-time, a geodesic, and that line happens to intersect the ground beneath our feet. This vision was at once breathtaking and disorienting. Newton's law of universal gravitation had seemed complete, accounting for the tides, the planetary orbits, and even predicting the return of comets. But there were anomalies it could not explain. The orbit of Mercury shifted slightly more than Newton's equations predicted, Light, which had no mass, should not have been affected by gravity, yet hints suggested it might bend near the Sunday-Einstein's equations accounted for these puzzles effortlessly. When in 1919 astronomers observed stars displaced during a solar eclipse, the bending of their light by the sun's curved space-time confirmed the theory in a triumph that captured headlines around the world. Suddenly, relativity was not only a theory but a revolution. The genius of Einstein's vision lay not only in its ability to explain anomalies, but in its profound reimagining of reality. Space and time were not absolute, fixed backdrops. They were dynamic, malleable, responsive to energy and momentum. A massive star slowed the passage of time around it. A rotating body dragged space-time around like a whirlpool. The universe itself could expand or contract under the weight of its contents. Reality was a dialogue. Matter told space-time how to curve, and space-time told matter how to move. The stage and the actors were intertwined, inseparable. But if this vision was elegant, it was also unsettling. How could one reconcile such a picture with the quantum world that was emerging at the same time? Quantum theory described particles and fields, probabilities and uncertainties, discrete packets of energy. General relativity described smooth curves, continuous geometries, deterministic motions. Each was internally consistent, yet the languages were alien to one another. The more we admired Einstein's achievement, the more we recognized the looming challenge it posed. If gravity was geometry, how could it fit into the quantum framework that described the rest of physics? Still, in its own domain, relativity was unmatched. It guided spacecraft across the solar system with pinpoint precision. It revealed the existence of black holes, where space-time curved so sharply that nothing, not even light, could escape. It explained the expansion of the universe itself, leading to the discovery of the Big Bang. It predicted gravitational waves, ripples in space-time from colliding black holes, which a century later were detected by laser interferometers stretching kilometers across. Each new confirmation strengthened Einstein's vision, elevating it to one of the greatest intellectual achievements in history. And yet, its very success deepened the puzzle. For if gravity is geometry, then it is unlike any other force. Electromagnetism, strong and weak forces, are mediated by fields and particles, describable within the quantum framework. Gravity alone is woven into the shape of reality itself. It is as though nature had written 3 laws in one language and a 4th in another. That dissonance hints at a deeper truth still concealed. Perhaps gravity's strangeness is not a flaw but a clue, suggesting it is not fundamental in the way we assumed. Einstein himself suspected his work was incomplete. He spent his later years seeking a unified theory, hoping to bring electromagnetism and gravity under one roof. He never succeeded, but his pursuit set the stage for generations of physicists to follow. Some seek to quantize gravity, to discover the elusive graviton. Others pursue radical ideas where gravity is not a force but an emergent phenomenon, the shadow of quantum information or entanglement. All of these efforts trace back to Einstein's insight that what we call gravity is geometry, and geometry may itself be an expression of something deeper. This is the power of Einstein's vision. It solved mysteries that had stood unsolved for centuries, reshaped our understanding of the cosmos, and revealed new horizons of mystery. To grasp why gravity might not be fundamental, we must understand this vision not as the final word, but as a chapter, luminous yet incomplete, in the larger story of physics. And in that story, the clash between relativity and quantum mechanics becomes the central drama. For while geometry explains the stars, quantum rules the atoms, and their worlds are not yet reconciled. Einstein's general relativity rests on a handful of deceptively simple principles, yet from them unfolds an astonishing tapestry. At its heart lies the equivalence principle, the idea that falling freely in a gravitational field is indistinguishable from floating in deep space. If you were sealed inside a closed room with no windows, you could not tell whether you were drifting far from any planet or falling toward Earth in free fall. This principle, tested again and again with increasing precision, says that gravity is not truly a force, but a condition of motion. In free fall, objects are not being pulled. They are simply following the natural flow of space-time. From this principle, Einstein built a geometric universe. Imagine a beam of light entering your sealed room. If the room is accelerating upward, the light's path will appear curved relative to you. If the room is falling freely in Earth's gravity, the same curve appears. The equivalence principle insists these two situations are the same. And from this, Einstein deduced that gravity bends light, not because light has mass, but because space-time itself is curved. In this way, he transformed a philosophical thought experiment into a profound physical law. The elegance of general relativity is that it reduces gravity to geometry. The equations describe how the presence of mass and energy distorts space-time, and how the curvature of space-time dictates the trajectories of objects. It is a dialogue written in mathematics, but its consequences can be visualized in every falling apple, every orbiting moon, every beam of starlight bent around a galaxy. We live not in a rigid container, but in a pliable arena, one that swells, stretches, and twists under the influence of matter and energy. The evidence for this vision is overwhelming. The orbit of Mercury, once a nagging anomaly, matches precisely when relativistic corrections are included. Light from distant stars bends as it passes massive bodies, a phenomenon confirmed not only during eclipses, but in the daily work of astrophysicists, who use gravitational lensing to map unseen matter. Time itself runs differently depending on gravitational potential, a fact that makes our global positioning satellites work correctly only because engineers include relativistic adjustments. The very functioning of modern technology depends on the truth of Einstein's insight. And yet the strangeness of this picture is easy to forget because of its success. It is tempting to accept it as the final word. But relativity contains within it seeds of tension. Black holes, predicted by the equations, are places where curvature becomes infinite. At the singularity, the laws break down. The Big Bang, the origin of cosmic expansion, is another singularity, a place where general relativity cannot speak. In both cases, we reach the boundaries of the theory, the edges where its predictions collapse. These boundaries tell us that Einstein's vision, as remarkable as it is incomplete. The incompleteness becomes sharper when we remember the quantum world. While relativity reigns on cosmic scales, quantum theory rules on atomic ones. Quantum fields explain the stability of matter, the interactions of particles, the energy levels of atoms. They operate with probabilities, discreteness, and uncertainty. Relativity, by contrast, is smooth, continuous, and deterministic. Put them together, and contradictions explode. Try to calculate the quantum fluctuations of space-time, and infinities appear that cannot be renormalized away, as they can in quantum electrodynamics. Attempt to describe the interior of a black hole with quantum rules, and paradoxes about information emerge. The two frameworks are like mismatched puzzle pieces, brilliant in isolation, but impossible to fit side by side. Einstein himself recognized the incompleteness. He did not live to see the quantum revolution fully integrated into physics, and in many ways he resisted its probabilistic interpretation. Still, he sought a deeper unity, believing the universe must ultimately rest on a coherent foundation. He did not find it, but his vision pushed others to continue. Today, physicists chase that unity through string theory, loop quantum gravity, holographic dualities, and more. Each approach attempts to reconcile the geometric elegance of relativity with the quantum world's discrete, probabilistic nature. None has yet succeeded completely, but each carries forward the question Einstein made unavoidable. To see gravity as geometry is to see it as unique among forces. This uniqueness explains its triumphs but also its failures. It explains why it accounts for planetary orbits and cosmic expansion, yet resists being quantized. And it is this uniqueness that drives us to ask whether gravity truly belongs alongside the other fundamental interactions, or whether it is something else entirely, a phenomenon emergent from a deeper substrate of nature. To move forward, we must place relativity and quantum theory face to face, to examine their conflict and the challenges that arise when gravity meets the quantum world. That confrontation is the next step in our journey. Einstein's curved spacetime remains one of the most powerful and precise descriptions humanity has ever discovered. We rely on it to guide spacecraft across the solar system, to predict the merger of black holes billions of light years away, to understand the very expansion of the cosmos. And yet, the very clarity of the theory forces us to confront its boundaries. It works astonishingly well wherever masses are large, but spacetime is not too small. When the stage is stretched across galaxies or wrapped around stars, relativity sings with perfect harmony. But when we turn our gaze inward, toward the smallest scales where quantum rules dominate, the music falters. Take the example of black holes. According to relativity, they are inevitable when enough mass collapses into a small enough region. Space-time folds inward until escape becomes impossible. At the center lies the singularity, a point where density becomes infinite, and the equations themselves lose meaning. Physics cannot tolerate infinities as answers. They are signposts that say our description has reached its limit. When quantum mechanics is considered, we expect those infinities should be tamed. Yet no one has found a way to reconcile the two pictures cleanly. Instead, we are left with paradoxes. Hawking radiation, predicted by combining relativity with quantum field theory, suggests black holes evaporate. But if they do, what happens to the information that fell inside? Relativity insists it cannot escape. Quantum mechanics insists it cannot be destroyed. Both cannot be right at once. The same clash arises when we look at the origin of the universe. Relativity describes a cosmos, expanding from an initial singularity, the Big Bang. But again, the singularity is a place where the laws fail. Quantum theory must matter here, since the early universe was unimaginably small and dense. Yet relativity cannot incorporate quantum principles without shattering. We stand before two pillars of physics that refuse to join at their foundations. That refusal is not a minor detail. It is the central challenge of modern theoretical physics, and so gravity remains an outlier. The electromagnetic, weak, and strong forces all submit to quantum description, mediated by exchange particles, unified within the Standard Model. Gravity alone resists, standing apart as geometry, as curvature, as something that seems beyond quantization. Perhaps this is why it has been so hard to unify. Perhaps it is not meant to be quantized because it is not fundamental in the first place. If gravity is emergent, then trying to capture it as a quantum particle may be like trying to bottle a rainbow. You can analyze the light, but the arc itself is an appearance born of deeper conditions. This idea, unsettling though it may be, grows stronger the more we examine the dissonance. Gravity's universality, its weakness, its geometric nature, its incompatibility with quantum mechanics, all suggest it may belong in a different category than the other interactions. It is both indispensable and incomplete, both elegant and fragile. It describes our universe with astonishing success, yet whispers that it is not the whole story. Einstein's vision changed everything. He taught us to see space-time as pliable, as curved, as alive with interaction. He showed us a universe where geometry replaces force, where mass and energy sculpt the very arena of existence. His equations have passed test after test, from the orbit of Mercury to the detection of gravitational waves. They remain pillars of science, monuments to human understanding. And yet, like Newton's before them, they may not be the final word. They may be a chapter, brilliant but incomplete, in a larger narrative. To grasp the true nature of gravity, we must now bring relativity face to face with quantum theory. Only in that confrontation can we see the depth of the problem and the hints of possible solutions. In that collision lies the possibility that gravity is not fundamental, that it emerges from the quantum world rather than standing beside it. The next chapter is that collision, where Einstein's smooth geometry meets the granular probabilities of the quantum realm, and where our familiar stranger once again resists our attempts to understand it fully. At first glance, it seems natural to imagine that if all other forces can be described within the framework of quantum theory, then gravity should too. After all, electromagnetism, the weak force, and the strong force all find their home in quantum field theory. Their carriers, the photon, the W and Z bosons, and the gluons, can be produced, detected, and calculated with astonishing precision. The triumph of the Standard Model rests on this union between forces and quanta. It would seem only natural to add gravity into this family portrait, with its own particle, the graviton, playing the role of mediator. And yet every attempt to do so runs into paradox and impossibility. To see why, we must recall what quantization means. In quantum theory, forces are not continuous fields stretching smoothly across space. They are quantized excitations of underlying fields, exchanged in discrete packets. A photon is not just a convenient label for light, but a particle, a quantum of the electromagnetic field. By analogy, if gravity were a fundamental force, its quanta would be gravitons, massless particles, with spin 2. These hypothetical particles would ripple through space-time, carrying gravitational influence from one place to another. In principle, their existence would let us calculate gravitational interactions, the same way we do with electromagnetism. But here the trouble begins. Gravitons have never been detected, and there are good reasons why. Gravity is fantastically weak compared to the other forces. To detect a single graviton with certainty would require a detector so massive it would collapse into a black hole under its own weight. In practice, this means direct detection is impossible. Gravity announces itself not through individual particles, but through vast accumulations of mass. The theoretical framework of gravitons remains an elegant abstraction with no experimental foothold. Even deeper problems arise when we try to apply the machinery of quantum field theory to gravity. The calculations yield infinities that cannot be renormalized away. In quantum electrodynamics, similar infinities appear, but clever techniques allow us to absorb them into redefined quantities, giving predictions that match experiment to 12 decimal places. With gravity, the infinities are uncontrollable. The theory breaks down, refusing to give sensible answers. This is not a minor technical detail, but a sign of something fundamentally wrong. Black holes bring these tensions into sharp relief. General relativity predicts them as inevitable when massive stars collapse. Quantum theory, applied to the curved space-time around them, predicts Hawking radiation, a slow evaporation of black holes through quantum effects near the horizon. This evaporation implies that black holes can vanish entirely. But if they do, what happens to the information that fell into them? Relativity says it is trapped forever. Quantum theory insists information cannot be destroyed. The conflict is stark, and it remains unresolved. This is the infamous information paradox, a clash not only of equations but of principles at the heart of physics. The early universe presents another battlefield. General relativity describes a singularity at the Big Bang, a point where space-time curvature becomes infinite, and the theory fails. Quantum theory insists that on scales so tiny, uncertainty and fluctuations dominate, smoothing out infinities. Yet attempts to merge the two pictures run into contradictions. Neither relativity nor quantum theory alone can describe the birth of the cosmos. Something deeper is required. The clash between gravity and quantum mechanics is more than an academic puzzle. It suggests that our current categories may be wrong. Perhaps gravity cannot be quantized because it is not fundamental. Perhaps what we call gravity is a large-scale phenomenon, like temperature or pressure, arising from the collective behavior of more basic ingredients. If so, the search for gravitons may be a search for something that does not exist, like looking for particles of heat instead of molecules of gas. And yet we cannot abandon gravity either. It remains essential for describing planets, stars, galaxies, and the structure of the universe itself. Its predictions have been confirmed in countless tests. The question is not whether gravity is real, but whether it is fundamental. If it is emergent, then general relativity is not the final law, but an approximation, a pattern that emerges from deeper quantum processes. The task of physics is then not to quantize gravity, but to uncover the substrate from which it arises. The failure to reconcile relativity and quantum mechanics is sometimes portrayed as a crisis, but it may also be an opportunity. It may be nature's way of telling us we are asking the wrong question. For nearly a century, physicists have tried to force gravity into the same mold as the other forces. Perhaps it belongs in another category altogether. The persistence of infinities, singularities, and paradoxes may be clues pointing us toward a radical rethinking. If gravity is not fundamental, then what is it? To answer that, we must broaden our imagination. Physics already knows of phenomena that appear fundamental, but are not. Heat emerges from molecular motion. Pressure emerges from particle collisions. Could gravity be similar, an emergent phenomenon that only looks like a fundamental force? This question leads us into the realm of emergent physics, where familiar laws arise from deeper structures, and where gravity itself may be no more fundamental than the warmth we feel from the fire. The conflict between gravity and quantum mechanics grows sharper the more closely we examine their domains. In relativity, space-time is smooth, continuous, a fabric that can stretch and bend, but not break into discrete units. In quantum theory, reality is granular, with energy levels quantized, fields fluctuating with irreducible uncertainty, and outcomes determined only probabilistically. These worldviews are not simply different, they are contradictory. Try to describe space-time itself with quantum rules, and the mathematics erupts into infinities. Try to treat gravity as just another field in the quantum family, and the framework collapses. Many attempts have been made to bridge this gap. Quantum field theory on curved space-time is one such approach. It applies quantum rules to matter fields while leaving space-time classical. This works in limited domains, giving us predictions like Hawking radiation, but it is incomplete because it treats gravity differently from everything else, leaving space-time immune to quantization. Other approaches, like string theory, attempt to describe all particles and forces as vibrations of tiny one-dimensional strings, with gravity emerging naturally as one of the modes. String theory has produced deep insights, such as holographic dualities, but it remains unproven and difficult to test. Loop quantum gravity, another approach, attempts to quantize space-time itself, describing it as a network of discrete loops. It avoids some infinities but has not yet shown how smooth space-time emerges at large scales. Each of these programs reflects the same underlying unease. We are trying to force gravity into the same category as the other forces, but the universe resists. Unlike the photon or gluon, the graviton cannot be detected. Unlike quantum fields, space-time refuses to yield to renormalization. The mathematics itself seems to hint that gravity may not be a force in the same sense as the others. It may be the shadow of something deeper, an emergent property of quantum information or entanglement, rather than a particle-mediated interaction. The paradoxes multiply when we consider black holes in more detail. The event horizon, the boundary beyond which nothing can return, is not a physical surface, but a feature of space-time geometry. Hawking showed that quantum effects near the horizon cause pairs of particles to appear, with one falling in and the other escaping as radiation. Over unimaginable spans of time, This process causes the black hole to shrink and eventually evaporate. But if the black hole vanishes, what happens to the information about the matter that once fell in? Relativity says it is lost beyond the horizon. Quantum mechanics says information is conserved. Both cannot be true. This conflict has become one of the most profound puzzles in physics, a riddle that continues to drive research today. Cosmology presents another front in this struggle. The early universe, compressed into an incredibly dense state, should be described by both relativity and quantum theory at once. Relativity predicts a singularity, an infinite density where the laws fail. Quantum mechanics suggests fluctuations, uncertainty, and perhaps a smoothing of that singularity. But without a coherent theory that unifies the two, we cannot say for sure. The very origin of the cosmos lies beyond our current understanding. This is not just a gap in knowledge, it is a sign that our frameworks themselves may need to be reimagined. One reason gravity may be so resistant to quantization is its universality. It couples to all forms of energy equally, with no exceptions. Photons feel it, neutrinos feel it, massive particles feel it. The electromagnetic force acts only on charged particles. The strong force acts only within nuclei. But gravity ignores such distinctions. This universality is what makes it so powerful on cosmic scales. It is also what makes it so hard to treat as just another field. When everything gravitates, the rules of separation and specialization that help us describe other forces break down. Gravity is the conversation of the entire universe at once, not the local exchange of quanta, and so the suspicion grows that gravity may not be a force at all in the fundamental sense. It may be more like temperature or pressure, quantities that feel fundamental in daily life, but dissolve into collective effects when viewed at the microscopic scale. Heat is not a substance, but the jostling of atoms. Pressure is not a field, but the collisions of molecules. Gravity may be the large-scale echo of deeper quantum realities, a pattern that emerges from the fabric of information itself. The possibility is unsettling, for it would mean one of the four great forces is not truly a force. It would mean our picture of the universe, so carefully constructed, needs to be redrawn from the ground up. Yet this is also the kind of radical shift that has marked every great advance in physics. To imagine gravity as emergent is not to deny its importance, but to place it in a new context, as a phenomenon that reveals the hidden architecture of reality. The next step in our journey is to explore the concept of emergence itself. Physics has long known that familiar laws can arise from deeper structures. Heat, sound, and elasticity are all emergent phenomena, appearing only when vast numbers of particles act together. If gravity belongs in this category, then its mysteries may be resolved not by forcing it into the quantum mold, but by recognizing it as a consequence of something more fundamental. To grasp this possibility, we must look more closely at how emergence works in physics, and how it may provide a template for rethinking gravity itself. The difficulty of reconciling gravity with quantum mechanics is not a small flaw in our theories, but a gaping fracture at the foundation of modern physics. It is as if we have built two towering cathedrals, each magnificent in its own right. Yet when we try to connect them, the arches collapse and the walls refuse to meet. General relativity explains the large-scale structure of the cosmos with unmatched precision. Quantum theory governs the small scale with uncanny accuracy. But at the frontier where the very large and the very small collide, such as inside black holes or at the beginning of the universe, neither cathedral can stand. The collapse of the mathematics there is a signal, an invitation to search for something deeper. Physicists have tried to tame this frontier in many ways. They have attempted to build a quantum field theory of gravity, only to find the infinities proliferate beyond control. They have imagined strings vibrating in higher dimensions, in which gravity appears not as a force, but as one of many resonances of a deeper structure. They have proposed networks of discrete loops, from which space-time itself might emerge. Each approach captures part of the truth, but not the whole. Each promises a glimpse of unity, yet leaves critical questions unanswered. The paradoxes sharpen when we consider not only the singularities of relativity, but also the fabric of space-time itself. Quantum mechanics suggests that on the smallest scales, space-time should not be smooth at all, but foamy, jittering, uncertain. Virtual particles would flicker in and out of existence, creating fluctuations in geometry itself. But relativity insists on continuity, on smooth curves and well-defined geodesics. The clash is stark. If space-time is smooth, quantum uncertainty is denied. If space-time is foamy, relativity collapses. We cannot have both pictures at once, and yet, both are indispensable. Even time itself becomes suspect in this struggle. In relativity, time is a dimension, intertwined with space, flowing differently depending on velocity and gravity. In quantum theory, time is an external parameter, a background against which probabilities evolve. The two treatments are incompatible. One makes time dynamical, the other makes it fixed. Perhaps the greatest clue that gravity is not fundamental is this tension over time itself. If time is emergent, then gravity, which is tied so deeply to the geometry of space-time, may be emergent as well. It is tempting to imagine that the problem is merely technical, that with clever mathematics or more powerful computers, the rift will close. But history suggests otherwise. When physics has faced contradictions this deep, the resolution has always required a conceptual leap. Newton's mechanics could not explain the orbit of Mercury until Einstein reimagined space and time. Classical thermodynamics seemed fundamental until statistical mechanics revealed it as emergent from atoms. In the same way, the conflict between gravity and quantum theory may be pointing us toward a radical shift, one that will make us rethink the very notion of fundamentality. This is why so many now entertain the possibility that gravity is emergent. The failures to quantize it, the paradoxes of black holes, the singularities of the Big Bang, the clash of time between relativity and quantum mechanics, all converge on the same suspicion. Gravity may not be an elementary interaction to be united with the others, but the large-scale manifestation of something deeper, perhaps rooted in quantum information, entanglement, or thermodynamic principles. If this is true, then our search for gravitons may be as misguided as an ancient search for the substance of heat. Just as the concept of caloric gave way to the molecular theory of temperature, our concept of gravity as a force may give way to a theory of gravity as a pattern. This would not diminish its grandeur, but deepen it. It would mean that every orbit, every falling stone, every bending of light is not the work of a fundamental force, but the visible signature of the hidden machinery of the universe. And so we reach the threshold of a new idea. To understand why gravity might not be fundamental, we must first understand what it means for a phenomenon to be emergent. Physics offers many examples, from heat to pressure to elasticity, where the whole is more than the sum of its parts. In the next step of our journey, we will explore these cases of emergence, not as digressions, but as essential models for how gravity itself may arise. The familiar stranger may turn out to be an illusion, a grandeur woven from deeper threads, waiting to be revealed. When we speak of something as fundamental, we mean it cannot be broken down into simpler parts. Yet much of what we experience in daily life is not fundamental at all, but emergent. Heat feels like a basic property of matter, yet we know it arises from the ceaseless jostling of atoms. Pressure feels like a direct attribute of air or water, yet it is nothing more than the statistical average of countless molecular impacts. Sound waves roll across landscapes and through oceans as if they were entities in their own right, yet they are patterns of compression and rarefaction, collective motions of vast numbers of particles moving together. Emergence is one of the most profound lessons of physics. What feels primary often dissolves into something deeper. Consider heat in more detail. To a child, heat seems as real as light or water. It burns the hand, it cooks food, it radiates from the fire. For centuries, natural philosophers believed heat was a substance, a fluid called caloric, that could flow from one body to another. This view made sense because heat seemed to move, to be conserved, to spread. But the caloric theory collapsed in the 19th century when experiments revealed that heat is not a substance, but motion. Every atom in matter vibrates, rotates, and collides. What we call heat is the average of this microscopic chaos. At a higher temperature, the atoms move more vigorously. At a lower temperature, they move more sluggishly. Heat is real, but it is not fundamental. It emerges from the collective behavior of matter's smallest components. Pressure tells a similar story. When you inflate a balloon, you feel the air pushing outward. It seems like pressure is a continuous property of the gas itself. Yet in reality, pressure is the sum of countless impacts of molecules colliding with the balloon's surface. Each molecule is invisible to us, each impact imperceptible, but together they create the sensation of pressure. If we could somehow freeze every molecule in place, pressure would vanish instantly. It has no existence apart from the motions of particles, yet we treat it as a real, measurable quantity. This is the essence of emergence. Sound, too, is emergent. When we hear a violin note or the crash of waves, it feels like sound is a substance traveling through the air or water. In truth, it is a coordinated pattern of particle displacements. Air molecules collide with one another, passing along tiny nudges that build into waves. Our ears detect these waves and our brains render them as tones, pitches, and voices. There is no fundamental particle of sound. It is the music of molecules moving together. The history of science is filled with such revelations. Electricity was once imagined as a fluid. Light was once thought to be a vibration of an invisible medium called the ether. Each time, careful experiments revealed that the familiar phenomenon was not fundamental but emergent, born of deeper structures. Each time, the revelation was not a diminishment but an enrichment, expanding our understanding and connecting seemingly disparate domains. Emergence is powerful because it creates new levels of reality. From the simple rules of molecules arise the complex behaviors of fluids. From the interactions of neurons arise the mysteries of thought. From the bonds of atoms arise the architectures of life. The emergent levels are real, measurable, and often indispensable for our survival. Yet they are not written into the most basic laws. They arise when vast numbers of components interact in ways that produce new patterns. If gravity is emergent, then it may belong to this same category. What feels like a fundamental pull may in fact be the large-scale echo of microscopic processes. The analogy is not perfect, but it is provocative. Heat was once thought to be a basic property of matter until we saw the atoms beneath it. Gravity may be seen as a basic force until we glimpse the quantum structures beneath it. If so, then the familiar pull that guides planets and holds us to Earth may be as emergent as temperature, as collective as pressure, as pattern-driven as sound. To explore this possibility, we must take the idea of emergence seriously. We must see how macroscopic laws can arise from microscopic rules, how order can arise from chaos, how simplicity can emerge from complexity. For in these lessons lies the possibility that gravity is not a bedrock, but a surface, not a fundamental force, but a phenomenon that emerges from the deep architecture of the universe. And it is here that bold thinkers like Jacobson, Verlinde, and many others have begun to push, crafting visions where gravity is the thermodynamics of space-time, the entropy of information, the geometry of entanglement. But before we dive into those modern visions, we must grasp the philosophical shift emergence requires. To accept that something as central as gravity might not be fundamental is to accept that our perspective on reality is always provisional. It is to see that nature often hides her secrets in plain sight, disguising deep truths as familiar experiences. It is to recognize that what we call fundamental may be only the beginning of the story, and that the true foundations lie deeper still. Emergent phenomena are everywhere once we learn to recognize them. The circulation of air in the atmosphere produces winds and storms that we can chart and predict, but these are not fundamental entities. They arise from the collective dance of molecules driven by differences in temperature and pressure. A hurricane feels like a vast, living force, yet it is no more than physics playing out on a colossal scale. In the same way, The shimmering of a rainbow feels like a property of light itself, yet it emerges from the refraction and reflection of countless water droplets. What looks simple and fundamental is often the product of hidden complexity beneath. Even the solidity of matter, which feels so absolute to our touch, is emergent. Press your hand against a wall and you feel resistance, as if the wall possesses a fundamental property of hardness. But that resistance arises from the electromagnetic repulsion of electrons in your hand and the wall. Atoms are mostly empty space. The solidity we rely on is an emergent effect of quantum forces that prevent atoms from occupying the same state. Matter feels solid, not because it is filled, but because of the rules of quantum mechanics playing out invisibly. Solidity is emergent, and yet it defines our entire experience of the physical world. Water offers one of the clearest illustrations of emergence. A single molecule of H2O has no wetness, no viscosity, no surface tension. It is simply a tiny bent structure of oxygen and hydrogen atoms. But gather trillions upon trillions of them, and entirely new properties appear. Wetness is not contained in any one molecule, but in the collective behavior of many. Ice, liquid water, and steam are phases that emerge depending on temperature and pressure. These are real, measurable properties, yet they exist only in the aggregate. If you insist that wetness must exist in a single molecule, you will never find it. If you insist that gravity must exist in a single particle, you may likewise be misled. Biology adds further testimony to the power of emergence. A single neuron does not think, does not dream, does not remember, but link billions of neurons in intricate networks and consciousness arises. We can measure electrical activity. We can map neural circuits, but the sensation of thought, the awareness of self, is an emergent property of the system as a whole. Consciousness is real, undeniable, yet it is not fundamental in the same sense as electrons or quarks. It emerges from their collective organization in the brain. The beauty of emergence is that it creates new realities that feel autonomous, even though they are built from simpler rules. Music is not a property of vibrating strings alone, but of the patterns and harmonies they create together. Traffic jams are not properties of cars themselves, but of the collective flow of many vehicles on a road. Markets are not reducible to individual traders, but emerge from the interactions of thousands of choices. At every level of scale, new phenomena appear that cannot be seen by studying the parts in isolation. If gravity belongs in this lineage, then it may be a phenomenon that emerges when space-time itself is treated not as a fundamental stage, but as a collective behavior of deeper elements. In such a view, space-time might be composed of microscopic degrees of freedom, as atoms compose matter, or neurons compose the brain. Gravity would then be the large-scale rule governing the emergent geometry, not a force written into the universe at the most basic level. Just as pressure and temperature describe averages of molecules, Einstein's field equations may describe averages of some deeper quantum entities. This does not diminish the power of relativity any more than the molecular view of heat diminished the power of thermodynamics. On the contrary, it elevates Einstein's equations to the status of effective laws, the surface description of a deeper structure. They remain true within their domain, just as the laws of thermodynamics remain true even though we know they are emergent. The difference is that we now suspect gravity's domain is not ultimate, but provisional. The laws we rely on may be shadows cast by something more fundamental. To prepare for this leap, we must understand that emergence does not make phenomena less real. Heat is real, pressure is real, sound is real. Their emergent status does not make them illusions. It only places them in a hierarchy of explanation. They are higher-level truths, arising from lower-level dynamics. Gravity may be exactly this kind of truth, real in its effects, indispensable in our lives, but not fundamental in its essence. It may be the great, emergent phenomenon of the cosmos. In the next step of our journey, we will see how this idea is not just speculation, but has been made precise. Ted Jacobson, in the 1990s, showed how Einstein's equations themselves can be derived from thermodynamic principles. His insight suggested that space-time has entropy, that horizons have temperature, and that gravity itself is the thermodynamics of space-time. This radical vision turns gravity from a fundamental force into an emergent phenomenon, just as heat is emergent from molecules. To understand how he reached this conclusion, we must look closely at the link between horizons, entropy, and the strange behavior of quantum fields in curved space-time. Emergence challenges our intuition because it blurs the boundary between what feels real and what is fundamental. When we touch a hot stove, the burn is undeniable. Yet the heat is not a substance flowing into our skin. It is the kinetic agitation of atoms vibrating more violently than those in our hand. When we press against a wall, the resistance is undeniable. Yet the solidity is not a fundamental property. It is the electromagnetic exclusion of electrons, refusing to occupy the same state. We experience the emergent reality directly, and only later learn that its foundation lies elsewhere. The lesson is humbling. Nature often hides her deepest truths beneath layers of familiar experience. If gravity is emergent, then our everyday encounter with it is like our encounter with heat or pressure. We feel it constantly. We rely on it. We describe it with equations that predict planetary orbits, tidal forces, and the dance of galaxies. Yet beneath this familiar reality may lie a deeper story, one in which gravity is not written into the fabric of nature, but arises from more basic principles. In such a vision, the smooth geometry of space-time would itself be an emergent construct, woven from microscopic degrees of freedom we cannot yet see directly. This shift in perspective would explain much of the difficulty we face in trying to quantize gravity. If gravity is not fundamental, then forcing it into the quantum framework of the other forces is like trying to quantize temperature or pressure. You can describe the motion of individual molecules with quantum mechanics, but temperature itself is not quantized. It is a collective measure, meaningful only when averaged over countless particles. In the same way, if gravity is emergent, its smooth equations are averages of deeper quantum realities. To seek a graviton as the particle of gravity may be as futile as seeking a particle of heat. The suspicion that gravity is emergent gains force when we consider the role of entropy and information in physics. Entropy, once a measure of disorder in thermodynamics, has been revealed as a measure of information at a deeper level. The second law of thermodynamics, that entropy never decreases, is not merely about heat flowing from hot to cold, but about information dispersing and becoming less ordered. If space-time itself has entropy, as black holes suggest, then gravity may be tied to information at the most fundamental level. The pull we feel could be the statistical tendency of microscopic states to maximize entropy, just as heat flows until temperatures equalize. These ideas are bold, but they are not mere speculation. They have been sharpened into precise arguments by physicists who saw the parallels between thermodynamics and gravity. The realization that horizons have entropy and temperature, that Einstein's equations can be derived from the laws of thermodynamics, gives substance to the notion that gravity is emergent. It transforms the analogy from a poetic suggestion into a mathematical program. And so we arrive at the threshold of Jacobson's insight. In 1995, he showed that Einstein's field equations could be reinterpreted as statements of thermodynamic balance, linking heat, entropy, and energy flow. This was a turning point, because it suggested that space-time itself behaves like a thermodynamic system, with microscopic degrees of freedom hidden beneath the smooth continuum of relativity. Gravity, in this view, is not fundamental at all, but the thermodynamics of space-time. The implications are profound. If gravity is emergent, then the fabric of the universe is woven not from geometry itself, but from something deeper, perhaps quantum information or entanglement. Our familiar stranger, the force we thought we knew, may be a surface phenomenon, the visible pattern of invisible structures. To follow this idea, we must turn to the thermodynamics of space-time, to Jacobson's vision, and to the growing evidence that gravity is the greatest emergent phenomenon of them all. In the mid-1990s, a quiet but revolutionary paper appeared that reframed the very meaning of Einstein's equations. The author was Ted Jacobson, a physicist with a gift for seeing connections that others overlooked. His proposal was radical in its simplicity. What if the equations of general relativity were not fundamental laws at all, but the thermodynamic equations of state for space-time itself? What if gravity was not a force written into the fabric of reality, but an emergent phenomenon like heat or pressure, arising from microscopic degrees of freedom hidden beneath the continuum we call space-time? Jacobson began with a striking observation. In thermodynamics, the relationship between energy, heat, and entropy defines the behavior of matter on large scales. We know that when energy flows across a boundary, entropy changes accordingly. We also know that this principle is universal, independent of the microscopic details of molecules. Jacobson realized that horizons in space-time, such as those around black holes or those perceived by accelerating observers, also behave thermodynamically. They possess entropy proportional to their area. They radiate with a temperature known as Unruh radiation. If horizons obey thermodynamic laws, then perhaps space-time itself is a thermodynamic system, and Einstein's equations are nothing more than the equation of state for that system. The concept of Unruh radiation is subtle but essential. In quantum field theory, the vacuum is not empty. It seethes with fluctuations, with particles and antiparticles appearing and annihilating too quickly to be observed directly. To an observer at rest, this activity is invisible, but to an accelerating observer, the vacuum glows with a faint thermal radiation. This is the Unruh effect, a sign that horizons and acceleration change the way observers perceive quantum fields. It was from this clue that Jacobson drew his inspiration. If every horizon carries a temperature and entropy, then perhaps thermodynamics is the key to understanding gravity. Jacobson's insight was to apply the first law of thermodynamics, the relation between heat, entropy, and temperature, to local Rindler horizons, which are the horizons experienced by uniformly accelerating observers. He considered the flow of energy across these horizons and the corresponding change in entropy. By demanding that the thermodynamic relation hold universally, he derived Einstein's field equations themselves. In other words, the very equations that describe how matter curves space-time can be reinterpreted as the thermodynamic equation of state for space-time. Gravity, in this view, is not fundamental, but emergent, arising from the statistical behavior of unseen microscopic degrees of freedom. This was a profound shift. For decades, physicists had debated whether gravity could be quantized like the other forces, whether gravitons could be detected, whether general relativity could be merged with quantum mechanics. Jacobson suggested an alternative. Perhaps we should stop treating gravity as a fundamental interaction and instead recognize it as a macroscopic manifestation of deeper laws. Just as heat emerges from atoms, gravity emerges from the microstructure of space-time. Einstein's equations are then not fundamental but effective, describing averages of microscopic processes we do not yet see. The elegance of this idea lies in its naturalness. Thermodynamics has always been a bridge between the microscopic and macroscopic, turning the random chaos of particles into predictable laws of temperature and pressure. To treat space-time in the same way requires us to imagine it has microscopic constituents, much as matter does. We may not yet know what these constituents are, but Jacobson's derivation suggests their existence. Without them, the thermodynamic interpretation makes no sense. With them, gravity becomes the grand emergent phenomenon of the cosmos. The impact of Jacobson's work was quiet at first, but its significance grew over time. It inspired new approaches to quantum gravity, new connections between information theory and space-time, and new visions of the universe, where geometry is not fundamental, but woven from deeper threads. It did not solve the puzzle of gravity, but it reframed it in a way that opened new doors. Instead of asking how to quantize gravity, it asked what microscopic system gives rise to it. Instead of treating gravity as a particle-mediated force, it treated it as a thermodynamic necessity. To grasp the radical nature of this proposal, we must linger on the meaning of horizon entropy. When black holes were first studied in detail, physicists realized they must have entropy proportional to the area of their event horizon. This was a strange and revolutionary idea. Entropy is usually associated with disorder, with the number of microscopic configurations a system can have. If black holes have entropy, then they must have microscopic states. But what are those states? What composes a black hole at the microscopic level? Jacobson's work did not answer this, but it built on the insight. If entropy belongs to horizons, then horizons are thermodynamic. And if horizons are thermodynamic, then so is space-time itself. This is the stage on which Jacobson's vision unfolded. Horizons with entropy, accelerating observers seeing Unruh radiation, the laws of thermodynamics applied not to molecules, but to space-time itself. From this stage emerged a new possibility, that gravity is not a fundamental interaction, but a statistical effect, the thermodynamics of space-time. It was a daring thought, and it opened a path towards seeing gravity not as a force, but as an emergent phenomenon. Jacobson's argument rests on the extraordinary realization that horizons are not merely mathematical boundaries, but physical entities with thermodynamic character. The first clue had come earlier from the work of Stephen Hawking, who showed that black holes radiate. According to classical relativity, nothing can escape from within the event horizon, but Hawking combined relativity with quantum field theory to show that quantum fluctuations near the horizon allow radiation to escape. This radiation is thermal, with a temperature inversely proportional to the mass of the black hole. The result was shocking. Black holes, the very symbols of inescapable gravity, glow faintly like hot coals. From this followed another surprise. If black holes have temperature, they must also have entropy. And indeed, Jacob Bekenstein had argued that the entropy of a black hole is proportional to the area of its event horizon. This is not like the entropy of a gas, which scales with volume, but instead with surface area. The entropy of a black hole is vast, dwarfing the entropy of ordinary matter. These ideas seemed bizarre at first, but Hawking's calculations cemented them. Black holes are thermodynamic systems, with entropy and temperature. Their horizons are not empty, but rich with hidden microstates. Jacobson saw that this was not an isolated curiosity, but a clue to the nature of space-time itself. If black hole horizons have entropy and temperature, perhaps every local horizon does. Accelerating observers, as the Unruh effect shows, perceive horizons even in empty space. To them, the vacuum glows with thermal radiation. These horizons too must have entropy and temperature. If that is the case, then thermodynamic relations are not restricted to black holes but apply universally. Space-time everywhere, not just near black holes, carries thermodynamic properties. Applying this insight, Jacobson imagined a small patch of space-time around any point. An accelerating observer in that patch perceives a horizon. He then applied the first law of thermodynamics, relating the change in entropy to the heat flow and temperature to this horizon. When he did so, the relation that emerged was Einstein's field equation. The law that describes how energy and momentum curve space-time turned out to be nothing more than the thermodynamic balance of entropy, temperature, and energy flow across horizons. The elegance of this derivation was breathtaking. Einstein's equations, which had seemed like fundamental laws, revealed themselves as equations of state, like the laws of thermodynamics. This shift in perspective carries immense implications. If Einstein's equations are equations of state, then space-time must have microscopic degrees of freedom. Just as temperature presupposes molecules, Space-time entropy presupposes underlying constituents. We may not yet know what they are, but their existence is implied. They might be strings, loops, qubits of information, or something beyond our current imagination. Whatever they are, they must exist, because without them, the thermodynamic interpretation is meaningless. Black hole thermodynamics reinforces this view. The 4 laws of black hole mechanics mirror the 4 laws of thermodynamics. The area of the event horizon never decreases, echoing the second law. The surface gravity of the horizon is constant, echoing thermal equilibrium. These parallels are not coincidences. They are signals that gravity is thermodynamics in disguise. They are hints that the geometry of spacetime is built from microscopic states we cannot yet see. For physicists, Jacobson's work was a jolt. It suggested that the difficulties in quantizing gravity might be due to a false assumption. We had treated gravity as fundamental, tried to quantize it like the other forces, and failed. But if gravity is emergent, then the failure is natural. We were quantizing the wrong thing. The task is not to quantize Einstein's equations, any more than we would quantize the equations of fluid dynamics. The task is to uncover the microscopic degrees of freedom that give rise to them. This perspective transforms our search for quantum gravity. Instead of asking how gravitons fit into the standard model, we ask what microstates make up spacetime. Instead of forcing gravity into the mold of fundamental interactions, we treat it as the great emergent phenomenon, the thermodynamics of the universe. Jacobson's insight gave physicists a new lens, one that connects black holes, horizons, entropy, and information into a single story. It is a story that points toward a deeper connection between gravity and information. If entropy is information hidden from us, then horizon entropy suggests that space-time hides information about its microscopic structure. When we lose track of that information, we see it as entropy. Gravity then emerges as the statistical behavior of these hidden degrees of freedom. This idea prepares the way for even bolder visions, where space-time itself is woven from quantum information and entanglement. But before we leap that far, we must pause to appreciate the depth of Jacobson's contribution. He showed that Einstein's equations are not sacrosanct laws of nature, but emergent balances, like the pressure laws of gases. He showed that space-time is not an inert continuum, but a thermodynamic system. He showed that gravity may be no more fundamental than heat. It was a revelation that shook the foundations of physics and opened the way to new ideas about the holographic nature of the universe and the entropic origin of gravity. The vision Jacobson offered was unsettling, because it shifted gravity from the realm of immutable law into the realm of emergent phenomena. To many physicists, this was both liberating and disorienting. Liberating because it provided a new way to think about the stubborn conflict between relativity and quantum mechanics. Disorienting because it suggested that what we had treated as one of nature's 4 fundamental forces might not be fundamental at all. If Einstein's field equations are simply thermodynamic relations, then gravity is not written into the fabric of reality but drawn from it, as temperature is drawn from molecules or pressure from collisions. The implications of this go far beyond black holes. Horizons appear whenever information is cut off from an observer, whether by acceleration, cosmic expansion, or gravitational collapse. Each horizon carries entropy. Each horizon radiates with a temperature. If these thermodynamic properties are universal, then the entire universe must be understood as a thermodynamic system. Gravity, then, is the manifestation of information flow and entropy change in space-time. It is not a separate interaction, but a collective effect of hidden degrees of freedom, degrees we cannot access directly, but that reveal themselves statistically. This way of thinking reshapes familiar paradoxes. The black hole information problem, for example, is no longer only about the fate of data swallowed by a singularity. It is about how microscopic states of space-time encode and release information, much as molecules encode and release energy in heat flow. The entropy of a black hole's horizon is not a mystery, but a clue that information is stored holographically on its surface. The evaporation of the black hole through Hawking radiation is then the gradual leakage of that information back into the universe, hidden in subtle correlations. What once seemed like a paradox may in fact be a window into the statistical mechanics of space-time. Seen in this light, Jacobson's insight is not a curiosity, but a turning point. It connects the geometry of relativity with the thermodynamics of entropy and the quantum fluctuations of fields. It ties together strands that had seemed separate, showing that black holes, horizons, entropy, and gravity are facets of the same phenomenon. It suggests that space-time itself is emergent, a smooth continuum, hiding a granular microstructure. And it raises the possibility that the true building blocks of the universe are not particles or fields, but bits of information, linked by entanglement into the fabric we call space-time. This radical vision also reshapes the question of unification. For decades, physicists had asked how to quantize gravity so that it could join the other forces in a grand unified theory. Jacobson's work suggested a different question. If gravity is emergent, then perhaps it is not to be quantized at all. Perhaps the task is to uncover the microscopic laws that give rise to space-time, and from which gravity naturally follows. In this view, the unification of physics may not come from forcing all forces into a single quantum field framework, but from recognizing that space-time itself is not fundamental and that gravity is its thermodynamic shadow. This perspective opened the door to other bold ideas. The holographic principle, which suggests that the information content of a region of space can be encoded on its boundary, found new support in the thermodynamic interpretation of gravity. Eric Verlinde's later proposal of gravity as an entropic force drew directly on Jacobson's insight, framing gravity as the tendency of systems to maximize entropy, and the idea that space-time itself may be built from networks of quantum entanglement found fertile ground in the recognition that entropy is central to geometry. Jacobson did not claim to have the final answer. He showed a possibility, a framework, a new way of interpreting old equations. But in doing so, he shifted the conversation. Gravity no longer had to be treated as a stubborn holdout refusing to fit into quantum theory. It could instead be seen as the great emergent phenomenon of the cosmos, a thermodynamic reality arising from the unseen architecture of space-time. This shift has inspired countless explorations, from holography to entanglement to emergent geometry. To stand in the wake of Jacobson's vision is to see gravity not as a stranger among forces, but as a signpost pointing to something deeper. It is to recognize that the familiar pull that governs our lives may be a surface phenomenon, a statistical shadow of a reality more profound. It is to glimpse a universe where space-time itself is woven from hidden degrees of freedom, and where geometry is not the foundation, but the appearance. In the next chapter, we will follow this thread into the holographic principle, where the very notion of dimensionality is turned inside out, and where gravity reveals itself not as fundamental, but as the projection of information, encoded on a boundary beyond our view. The story of gravity took another astonishing turn in the 1990s, when physicists began to realize that space-time itself might be holographic. The idea was bold, almost unthinkable. It suggested that everything we perceive in three spatial dimensions, all the volume of the universe, might in fact be a projection from information encoded on a lower dimensional boundary. Gravity, in this vision, is not fundamental, but the emergent geometry of that projection. This was the essence of the holographic principle, and it arose from the strange thermodynamics of black holes. The seed of the idea came from Jacob Bekenstein's insight that the entropy of a black hole is proportional to the area of its horizon, not its volume. This meant that the amount of information that can be stored in a region of space is bounded not by how much volume it contains, but by the surface area enclosing it. This was shocking, because in ordinary physics, information scales with volume. A box twice as large should be able to hold twice as much information. But black holes told us otherwise. Double the radius of a black hole and the entropy grows by a factor of 4. not 8. The information content is holographic, like a two-dimensional image that encodes a three-dimensional scene. Gerard 't Hooft and Leonard Susskind sharpened this insight into the holographic principle. They argued that the maximum entropy in any region of space is determined by its surface area measured in Planck units, the tiniest scales of length. If this is true, then the true degrees of freedom of the universe live not in the volume, but on the boundary. Our three-dimensional world is a projection, like a hologram. The idea was radical, but it solved puzzles about black hole information. If information is stored on the horizon, then perhaps it is never lost. Even when matter falls into a black hole, the horizon encodes it, and gravity is the way that encoding manifests itself. The holographic principle might have remained a provocative speculation, but in 1997, Juan Maldacena provided a concrete realization. He proposed a duality between a gravitational theory in a five-dimensional anti-de Sitter space and a conformal field theory without gravity on its four-dimensional boundary. This became known as the ADS-CFT correspondence. It was a precise mathematical equivalence. Every state in the gravitational bulk corresponded to a state in the boundary field theory, and vice versa. Gravity in the bulk was emergent from quantum interactions on the boundary. Space-time itself was built from information. This correspondence electrified the physics community. It was the first time the holographic principle was not just an idea, but a working framework. The implications were staggering. If gravity in a higher dimensional space could be equivalent to a quantum theory without gravity in fewer dimensions, then gravity was not fundamental. It was a reflection, a projection, an emergent property of deeper quantum laws. The smooth geometry of space-time was a mirage created by correlations on the boundary. The ADS-CFT correspondence is highly specific, applying to a universe with negative curvature, unlike our own. Yet it has become one of the most studied and fruitful ideas in theoretical physics. It provides a laboratory where questions about quantum gravity can be translated into solvable problems in quantum field theory. It offers hints about how black hole information is preserved. It shows that spacetime itself can emerge from quantum entanglement, and it gives powerful evidence that gravity is holographic, not fundamental. The philosophical shift here is enormous. If holography is true, then our experience of space and time is like watching a holographic image. It feels three-dimensional, but its origin lies on a two-dimensional surface. The bulk is emergent, the boundary fundamental. Gravity is the curvature of that emergent bulk. Not a basic force, but a large-scale expression of information encoded elsewhere. It is geometry woven from entanglement, not a force transmitted by a particle. This vision reshapes the meaning of reality itself. It suggests that the universe we inhabit is not the deepest layer of nature, but a projection from something beyond our perception. It suggests that the mystery of gravity may be resolved not by quantizing it, but by recognizing that it is not fundamental at all. Gravity, in this view, is the shimmering surface of information, the echo of quantum interactions, encoded on a boundary we cannot see. And so, from black hole entropy to the holographic principle to Maldacena's correspondence, gravity has been revealed again and again as something different, something emergent. Jacobson showed it could be seen as thermodynamic. Holography shows it can be seen as projection. Both point to the same conclusion. Gravity is not a fundamental force. It is the geometry of information, the thermodynamics of space-time, the hologram of quantum reality. In the next chapter, we will follow Eric Verlinde as he takes this idea further. He proposes that gravity itself is an entropic force, arising from the natural tendency of systems to increase entropy. His theory attempts to explain not only the nature of gravity, but also the mysterious phenomena attributed to dark matter. Whether right or wrong, Verlinde's bold vision deepens the suspicion that gravity is emergent, not fundamental, and that the universe is woven from information rather than pulled together by invisible strings. The holographic idea did not remain a mathematical curiosity confined to anti-de Sitter space. Physicists soon began to see deeper consequences, and the key was entanglement. In quantum theory, entanglement describes the strange correlation between particles or fields, where the state of one cannot be described without reference to the other. Entanglement is not a side effect, but the core of quantum mechanics. In the holographic context, it becomes the glue of space-time itself. Consider a region of space in the boundary theory. The entanglement entropy of that region is the measure of how much quantum information it shares with the rest of the boundary. In the ADS-CFT correspondence, this entropy is equal to the area of a surface in the bulk spacetime that hangs like a soap film across the boundary region. This is the Ryu-Takayanagi formula, and it suggests something astonishing. Spacetime geometry is determined by quantum entanglement. The area of bulk surfaces, which in relativity measures curvature and distance, is nothing but the measure of entanglement in the boundary theory. The shape of spacetime is the shape of entanglement. This was a profound realization. For centuries, geometry had been treated as the foundation of physics. Newton saw it as the stage. Einstein saw it as dynamic, curved by energy. But holography suggests geometry itself is not fundamental. It is emergent from quantum information. Gravity, in this picture, is the large-scale manifestation of entanglement patterns. When entanglement decreases, geometry tears. When entanglement increases, geometry knits together. Spacetime is a tapestry woven from quantum threads. This connection also gives new perspective on the black hole information paradox. If information is stored holographically on the boundary, then it is never truly lost, even if matter falls into a black hole. The horizon encodes it, the entanglement distributes it, and the bulk geometry reflects it. The paradox does not vanish, but it transforms. Instead of information being destroyed, it is scrambled and re-expressed in ways we are only beginning to understand. Holography also reshapes cosmology. If spacetime itself can be emergent from entanglement, then the Big Bang singularity may not be the beginning of everything, but the point where entanglement networks reached a minimum. The expansion of the universe may be understood as the growth of entanglement. The smoothness of spacetime may be the collective effect of countless correlations. Gravity then becomes not a fundamental force, but the statistical behavior of information itself. Even the weakness of gravity compared to other forces makes sense in this picture. If it is emergent, it is not surprising that it appears only as a large-scale residue, not as a fundamental interaction. It is diffuse, universal, and geometric, the way temperature is diffuse, universal, and statistical. The electromagnetic force is sharp and strong because it is mediated by fundamental particles. Gravity is soft and weak because it is emergent from correlations. The holographic principle remains one of the boldest ideas in physics. It suggests that the universe we experience is not the final layer of reality, but a projection, a hologram, encoded on a boundary beyond our sight. It suggests that gravity is not a particle-mediated force, but an emergent geometry. It unites thermodynamics, quantum mechanics, and relativity into a single vision, where information is the true currency of the cosmos. But the principle, while powerful, left questions unanswered. How exactly does entanglement produce the experience of a force? How does the tendency of systems to maximize entropy translate into the falling of an apple, the orbit of a planet, the lensing of light? To answer these, Eric Verlinde proposed that gravity is not only holographic, but entropic. It is the force that emerges when systems seek to increase their entropy. It is the most natural force of all, born not from particles or fields, but from the statistical drive of information. The holographic picture forces us to rethink what we mean by reality. If the contents of a volume of space can be fully encoded on its boundary, then the notion of space itself is emergent. We are accustomed to believing that events happen within space and time, as though they were containers. Yet, holography suggests the opposite. The container is not fundamental. It arises from the information that lives on a lower dimensional surface. Gravity, then, is the language through which this information expresses itself as geometry. The evidence accumulates most vividly in the study of entanglement. The Ryu Takayanagi formula showed that the area of certain surfaces in spacetime corresponds to entanglement entropy in the boundary theory. Later generalizations deepened this connection, revealing that the very dynamics of spacetime could be written in terms of information-theoretic quantities. In effect, Einstein's equations could be derived from the entanglement structure of the boundary. Geometry is the shadow of entanglement, and gravity is the curvature of that shadow. This connection gives us a new way to think about the unity of physics. In the traditional view, the forces of nature are distinct interactions carried by distinct particles. But in the holographic view, gravity is not an interaction at all. It is the collective behavior of information. The familiar pull we attribute to mass is the manifestation of entanglement patterns adjusting themselves. Gravity is not transmitted, but arises. It is as if the universe itself is a vast quantum code, and gravity is the emergent rule that holds the code together. The holographic idea also resolves puzzles that once seemed insurmountable. The black hole information paradox softens when we see information encoded on horizons. The cosmological puzzles of entropy and expansion take new form when we imagine spacetime itself as an entanglement network. Even the notion of locality, the idea that events influence only their immediate neighbors, becomes emergent rather than fundamental. In the holographic framework, non-local correlations of quantum information can give rise to the illusion of local geometry. What we call nearby and far away may itself be a product of entanglement. Yet, for all its elegance, holography leaves us with unfinished questions. If gravity is emergent from information, how do we connect this vision to the phenomena we measure, like planetary orbits, gravitational lensing, or the rotation of galaxies? How does the deep principle translate into the everyday experience of weight and fall? These are not trivial questions, because an emergent description must reproduce the familiar with precision. If gravity is not fundamental, it must nonetheless explain why it behaves so consistently as though it were. It was into this gap that Erik Verlinde stepped. Drawing inspiration from Jacobson and from the holographic principle, he proposed that gravity is an entropic force. In Verlinde's view, the reason masses attract each other is not because of a fundamental particle or field, but because of the statistical tendency of systems to maximize entropy. When matter shifts position, the information associated with it changes, and the resulting entropic gradient produces what we perceive as a force. In this framework, the pull of gravity is the universe's drive toward greater entropy, encoded holographically in the information structure of spacetime. Verlinde went further, suggesting that this entropic picture could explain not only ordinary gravity, but also the puzzling phenomena attributed to dark matter. If his theory is correct, then the missing mass in galaxies and clusters may not be unseen particles, but the manifestation of entropic gravity. It was a bold claim, controversial and debated, but it represented the next step in the journey. From thermodynamics to holography to entropy, the suspicion grows stronger. Gravity is not a fundamental force. It is an emergent phenomenon, the collective effect of information and entropy, the great illusion that holds the cosmos together. By the early 2000s, the suspicion that gravity might be emergent had taken deep root. Jacobson had shown that Einstein's equations could be seen as thermodynamic relations. The holographic principle and the ADS-CFT correspondence had revealed that spacetime itself could be encoded on a lower dimensional boundary, with gravity arising from quantum information. Yet there remained a pressing question. If gravity is emergent, then how does it show up in our everyday lives, as the familiar pull of an apple falling to Earth, or the steady orbit of planets around the Sun? How can a force so concrete be explained as an effect of entropy and information? It was Eric Verlinde who took the bold step of answering this question. In 2010, he published a paper that ignited both excitement and controversy. His claim was radical. Gravity is not a fundamental interaction at all, but an entropic force. Like the force you feel when stretching an elastic band, gravity emerges from the statistical tendency of systems to maximize entropy. When the position of matter changes, the information associated with it also changes. The resulting gradient in entropy produces a force, and that force is what we call gravity. Verlinde's argument was simple in spirit, though subtle in detail. He considered a holographic screen, a notional surface encoding information about the positions of matter. He applied the tools of thermodynamics and information theory, combining them with the holographic principle. By demanding consistency with entropy maximization, he showed that Newton's law of gravity emerges naturally. The inverse square law, which Newton had discovered centuries earlier, was not fundamental, but statistical. It was the macroscopic expression of information changing as matter rearranges itself. This was a profound claim because it reimagined gravity not as a fundamental force, but as an entropic necessity. Just as molecules tend to spread out to maximize entropy, just as heat flows to equalize temperature, matter attracts matter because that is the way information organizes itself. Gravity, in Verlinde's view, is no different in essence from these other entropic tendencies. It only feels fundamental because we experience it everywhere, but its root lies not in particles or fields, but in the deep logic of entropy. What gave Verlinde's proposal special resonance was its potential to explain the mysteries of dark matter. Astronomers had long observed that galaxies rotate faster than can be accounted for by visible matter. According to Newtonian dynamics and general relativity, stars at the edges of galaxies should orbit more slowly, yet they do not. To explain this, physicists had proposed the existence of dark matter, invisible particles that outnumber ordinary matter and provide the missing gravitational pull. Despite decades of searching, no such particles have been found. Verlinde suggested that, perhaps, they do not exist at all. Perhaps the excess gravitational effects are simply the result of entropic gravity. In 2016, he expanded his theory, showing that when the entropy associated with the universe's dark energy is taken into account, additional gravitational effects arise naturally. These effects mimic the behavior usually attributed to dark matter, explaining the anomalous rotation curves of galaxies without invoking invisible particles. Gravity, in this view, is emergent from information and entropy, and its apparent deviations at large scales are not new matter, but new rules of information. The response was electric and divided. Some hailed Verlinde's theory as a breakthrough, a bold alternative to decades of fruitless searches for dark matter particles. Others criticized it as incomplete, unable to explain all the evidence attributed to dark matter, such as the behavior of galaxy clusters or the cosmic microwave background. The debate continues, but what matters is not only whether Verlinde's specific model survives, but that it pushed the conversation forward. It gave physicists a concrete framework to test, to challenge, to refine. It showed that the idea of emergent gravity is not mere philosophy, but a research program with predictions. For the first time, emergent gravity theories could be brought face to face with astronomical data. Verlinde's model predicted specific deviations from Newtonian gravity at galactic scales. Observations of galaxy rotation curves and gravitational lensing could test these predictions. Some results have been encouraging, others less so. The theory is not yet complete, but it has opened a new path, showing that the idea of gravity as entropic force can be tested in the cosmos. What makes Verlinde's vision so compelling is not just its specific claims about dark matter, but its broader message. It insists that gravity is not fundamental, that the universe we experience is an emergent tapestry woven from entropy and information. It reframes our understanding of the cosmos, placing information at the foundation and gravity as its emergent expression. Whether or not his exact equations stand the test of time, the direction he points to is clear. Gravity may not be the deepest law. It may be the shadow of a deeper principle, the entropic drive of the universe toward ever greater information. And yet, Verlinde's proposal is not the end of the story. If gravity is tied to entropy, and entropy is tied to information, then we must ask, what is the true role of quantum entanglement? Increasingly, physicists have come to suspect that entanglement is the deepest link of all, that space-time itself is woven from networks of entanglement, and that gravity is the curvature of that network. To explore this possibility, we must look beyond entropic gravity to the strange world where wormholes and entanglement meet, where space-time is nothing more than information geometry. Verlinde's proposal struck at the heart of one of the greatest mysteries in modern astrophysics. For decades, dark matter had been the dominant explanation for why galaxies behave as they do. According to Newtonian dynamics and Einstein's relativity, the visible stars, gas, and dust in a galaxy are far too little to generate the gravitational pull required to hold the system together. At the speeds observed, galaxies should fly apart. To solve this, physicists invoked dark matter, an invisible substance that outweighs normal matter by a factor of about 5 to 1. The search for dark matter particles became one of the great quests of modern science. Enormous detectors were built underground, particle accelerators were tasked with producing them, and telescopes mapped their gravitational effects. And yet, despite decades of searching, no dark matter particle has been found. It was in this context that Verlinde's entropic gravity arrived like a thunderclap. Instead of postulating new matter, Verlinde argued that our understanding of gravity itself needed revision. He suggested that what astronomers attributed to dark matter might in fact be the natural consequence of gravity as an emergent force. When the entropy of space-time and the energy of dark energy are included, new terms arise in the equations of motion. These terms mimic the gravitational effects usually blamed on dark matter. In this view, galaxies rotate the way they do not because of unseen particles, but because gravity itself has emergent corrections on large scales. Verlinde tested his model against observed galaxy rotation curves. To a surprising degree, the results matched. Without invoking dark matter, his entropic framework reproduced the flat rotation profiles of spiral galaxies. For many physicists, this was electrifying. Here was a theory that did not require exotic particles, and that emerged naturally from information-theoretic principles. It offered a testable, falsifiable alternative to the dark matter paradigm. But as with all bold ideas, criticisms soon followed. While Verlinde's model captured galaxy rotation curves, it struggled with galaxy clusters. Observations of the Bullet Cluster, a collision of two galaxy clusters, had been considered one of the strongest pieces of evidence for dark matter. The gravitational lensing maps did not align with the visible matter, but instead with regions thought to contain dark matter. Verlinde's entropic gravity has difficulty reproducing such results. Critics argued that while his model was clever, it lacked the flexibility to explain all the evidence that dark matter explains. Another challenge came from cosmology. The cosmic microwave background, the afterglow of the Big Bang, carries imprints of the universe's earliest structure. The standard cosmological model, with dark matter included, reproduces those imprints beautifully. Verlinde's theory, in its current form, cannot yet match this level of detail. For many cosmologists, this is a decisive weakness. Without fitting the cosmic microwave background, any alternative theory remains incomplete. And yet, the importance of Verlinde's work is not diminished by these challenges. The history of science is full of early theories that were incomplete, yet transformative. What matters is that Verlinde showed that emergent gravity can produce testable predictions, He showed that the anomalies we attribute to dark matter can at least partly be explained without invoking unseen particles. He gave us a new perspective on gravity as entropic force, tied to information and entropy rather than fundamental particles. The controversy continues. Some experiments suggest that dark matter particles remain elusive but possible. Others suggest that the anomalies may indeed point to new physics in gravity. What is certain is that Verlinde forced physicists to rethink their assumptions. He reminded us that the failure to find dark matter may not be a failure of experiment, but a failure of concept. Perhaps we have been looking for something that does not exist, like searching for caloric, when the truth is molecular motion. The broader significance of Verlinde's proposal lies in its unification of ideas. It builds on Jacobson's thermodynamic gravity, on the holographic principle, and on the central role of entropy. It weaves these threads into a picture where gravity is not fundamental but emergent, not a force, but a drive of information. Whether or not his specific model survives, the direction it points to is profound. It points toward a universe where gravity is geometry born of entropy, where dark matter may be an illusion, and where the true foundation is information itself. But if entropy drives gravity, what is the medium in which this entropy lives? Increasingly, physicists have turned to quantum entanglement as the answer. Entanglement may be the fabric from which space-time itself is woven, with gravity as its emergent curvature. To follow this path, we must look at the strange proposal known as ER equals EPR, where wormholes and entanglement are revealed as two sides of the same coin. Verlinde's theory has continued to spark debate because it touches on some of the deepest tensions in modern physics. On one side stand the supporters of the dark matter paradigm, pointing to the overwhelming success of the standard cosmological model in fitting observations across scales. On the other side are those intrigued by the possibility that gravity itself needs revision, that the anomalies in galaxy rotation and lensing may be signals of emergent laws rather than hidden matter. Between these positions lies a landscape of questions about what we mean by fundamentality, what counts as evidence, and how bold we must be when nature resists easy answers. One of the strengths of Verlinde's framework is that it highlights the link between gravity and information. By tying gravitational attraction to entropy gradients, it reframes the motion of planets and galaxies as statistical outcomes of microscopic information flow. This fits elegantly with Jacobson's thermodynamic interpretation and the holographic principle. It places gravity squarely within the lineage of emergent phenomena, alongside temperature and pressure. In Verlinde's story, the universe is not held together by invisible particles or mysterious fields, but by the entropic drive of information encoded on holographic screens. Yet, this elegance is tempered by incompleteness. The theory has difficulty addressing cosmological data in full, especially the detailed anisotropies of the cosmic microwave background and the dynamics of large-scale structure formation. Critics point out that while the entropic force can mimic dark matter in galaxies, it falters in clusters and cosmology. Others note that Verlinde's equations are not yet derived from first principles but constructed to reproduce certain features. For emergent gravity to stand as a true replacement, it must be as predictive and universal as general relativity has proven to be. Still, the significance of Verlinde's proposal lies not only in its immediate successes or failures, but in the intellectual shift it represents. It pushes us to take seriously the possibility that gravity is not fundamental. It suggests that the stubborn failure to detect dark matter particles may not be an experimental oversight, but a conceptual clue. It shows that the phenomena of the cosmos can be reinterpreted through the lens of entropy and information. And it keeps alive the radical idea that space-time itself is emergent, that gravity is not a force, but a consequence. In this sense, Verlinde's entropic gravity stands alongside Jacobson's thermodynamic gravity and the holographic principle as part of a larger movement. All three suggest that gravity is an emergent phenomenon, tied not to particles but to information. All three point to entropy as the key, whether expressed in horizon area, holographic encoding, or entropic force. Together they form a new paradigm, one that challenges our deepest assumptions about space, time, and the forces that shape them. The debate is far from settled. Observations will continue to test Verlindi's predictions, just as they continue to constrain dark matter models. New telescopes and surveys will probe galaxy rotation, gravitational lensing, and cosmic structure with unprecedented detail. Whether emergent gravity can rise to these challenges remains to be seen. But even if the specific details of Verlindi's theory are revised or replaced, the broader lesson will remain. Gravity may not be what it seems. The next frontier in this journey lies with entanglement. If entropy drives gravity, and if entropy itself is a measure of hidden information, then we must ask, what kind of information? Increasingly, the answer appears to be quantum entanglement, the mysterious correlation that binds particles across space and time. Some physicists have proposed that space-time itself is constructed from entanglement, and that gravity is nothing more than the curvature of that entanglement network. This leads us to the bold idea known as ER equals EPR, where wormholes and entanglement are revealed as two faces of the same underlying reality. By now, a pattern has emerged. Each attempt to understand gravity at its deepest level points not toward particles or fields, but toward information. Jacobson showed that Einstein's equations behave like thermodynamics. The holographic principle suggested that spacetime is a projection of information on a lower dimensional boundary. Verlinde argued that gravity is an entropic force, driven by the natural tendency of systems to maximize entropy. Each of these visions places information, not geometry, at the foundation. The next step is to ask what kind of information underlies spacetime itself. The answer, increasingly, seems to be quantum entanglement. Entanglement is one of the strangest and most profound features of quantum mechanics. When two particles are entangled, their properties become linked, no matter how far apart they are. Measure the spin of one, and the spin of the other is instantly determined, even across light years. Einstein once called this spooky action at a distance, but it is now a well-established fact. Entanglement is not a passing curiosity. It is the foundation of quantum computing, quantum cryptography, and the very structure of quantum theory itself. In the context of gravity, entanglement takes on an even deeper role. The holographic correspondence showed that space-time geometry is linked to entanglement entropy. The Ryu-Takayanagi formula revealed that the area of certain surfaces in space-time corresponds to the amount of entanglement in the boundary theory. This means that geometry is nothing but entanglement made visible. If entanglement disappears, geometry itself falls apart. If entanglement is strong, geometry is smooth and connected. Space-time is literally woven from quantum correlations. This idea was pushed further by Juan Maldacena and Leonard Susskind in a bold proposal known as ER equals EPR. ER stands for Einstein-Rosen, the physicists who described wormholes, or Einstein-Rosen bridges. EPR stands for Einstein, Podolsky, and Rosen, who formulated the famous paradox about entanglement. Maldacena and Susskind proposed that these two are not separate at all. Wormholes and entanglement are two descriptions of the same phenomenon. Every entangled pair of particles is connected by a tiny wormhole, invisible and undetectable, but real in the geometry of spacetime. If this is true, then spacetime itself is a vast network of entanglement. Every correlation between quantum systems knits geometry together. The strength of entanglement determines the shape of space. Gravity emerges from the curvature of this entanglement network. It is not fundamental but collective, a manifestation of how information is distributed. The universe is not built from particles arranged in space. Space itself is built from entangled particles. This vision is as radical as it is beautiful. It dissolves the old puzzle of how gravity fits with quantum mechanics. Instead of forcing gravity into the quantum mold, it makes gravity an emergent property of entanglement. It explains why space-time and quantum theory, which once seemed irreconcilable, are in fact inseparable. Geometry is the large-scale reflection of entanglement. Gravity is the force that geometry expresses. But the ER equals EPR idea does more than unify concepts. It provides tools for solving real problems. The black hole information paradox, for example, can be reinterpreted if black hole interiors are connected to the outside world through entangled wormholes. The puzzle of how information escapes may be resolved by recognizing that entanglement is the channel. What seemed paradoxical under the old view of space-time becomes natural under the new. Quantum entanglement also offers a new way to think about cosmology, the expansion of the universe, the smoothness of space-time, and even the arrow of time may all be linked to the growth and distribution of entanglement. If geometry is entanglement, then the history of the cosmos is the history of quantum correlations spreading and reorganizing themselves. Gravity is the script written by these correlations, not a force separate from them. The more we explore, the more the idea takes hold. Gravity is not fundamental. It is the curvature of an emergent geometry woven from entanglement. Space-time itself is not fundamental. It is the tapestry of information, and the universe we inhabit is not built from objects within space, but from correlations that create the very notion of space. In the next part, we will look more closely at how entanglement networks construct space-time, how geometry emerges from information, and why this vision may finally reconcile the strange marriage of gravity and quantum mechanics. The idea that entanglement weaves the fabric of space-time is not only philosophical, but mathematical. Physicists have constructed explicit models where geometry emerges from networks of entanglement, showing in detail how correlations between quantum states can generate the smoothness we associate with space-time. These models use tools from quantum information theory and condensed matter physics, areas far removed from Einstein's original vision, yet they arrive at the same destination. Curvature, distance, and even gravitational dynamics arise naturally when entanglement is arranged in the right way. One such approach is the tensor network model. A tensor is a mathematical object that encodes correlations between many degrees of freedom. When arranged in networks, these tensors can describe complex quantum systems. Remarkably, certain tensor networks reproduce the geometry of curved spaces. The entanglement structure built into the network dictates the shape of the emergent space. A highly entangled network produces a continuous, connected geometry. Reduce the entanglement, and the geometry fragments, breaking into disjoint pieces. This vividly illustrates how space can arise from information. These networks mirror the logic of the holographic principle. The bulk geometry is encoded in the entanglement pattern of the boundary system. The famous Ryu-Takayanagi formula, which relates entanglement entropy to the area of surfaces in space-time, emerges naturally from these constructions. In this sense, geometry is not an assumption but a consequence. It is the visible shadow cast by invisible correlations. Gravity, as the dynamics of geometry, is then a higher-level description of the information flows within the network. The implications are staggering. If space is emergent, then locality itself is emergent. The idea that events influence only their nearby neighbors, a cornerstone of physics, becomes a product of the entanglement pattern. What we call distance is simply a measure of how entangled two systems are. Strong entanglement corresponds to closeness, weak entanglement to separation. Wormholes in this language are nothing but shortcuts in the entanglement network, linking distant regions of space through hidden correlations. The ER equals EPR idea finds natural expression here. Entanglement and geometry are two sides of the same coin. This vision also provides new hope for resolving the clash between relativity and quantum mechanics. Instead of forcing space-time to obey quantum rules, it shows that quantum rules generate space-time. Gravity is no longer an outsider among the forces but the large-scale behavior of entanglement. Quantum mechanics and relativity are not rivals but partners. one describing the microstructure of correlations, the other describing the emergent geometry they create. But perhaps the most tantalizing implication is that the universe is, at its core, informational. The deepest layer is not matter, energy, or even space, but entanglement. Space-time is an illusion crafted by correlations. Gravity is the expression of how those correlations bend geometry. Reality itself is a quantum code, with error correction built into the very structure of space. In this light, the laws of physics become the rules of information processing, and the universe becomes a vast computational system. This way of thinking is radical, but it offers clarity where paradox once reigned. The information paradox of black holes becomes a problem of entanglement bookkeeping. The singularity at the Big Bang may be reinterpreted as a special configuration of correlations. Even the arrow of time may arise from the growth of entanglement, as information spreads irreversibly across the network. Yet questions remain. How exactly do the microscopic laws of entanglement give rise to Einstein's equations on large scales? Can these models reproduce all the precision tests of relativity, from gravitational waves to lensing to cosmology? And if space-time is a code, what is the computer that runs it? These are open questions, but they point toward a future where physics is redefined as the study of information at every scale. The next step in our journey will be to examine how these entanglement-based ideas are being tested, both in theoretical models and in experiments. Can we see evidence that space-time is emergent? Can we link laboratory quantum systems to the geometry of space? The search for proof will determine whether gravity is truly fundamental or the greatest illusion nature has ever woven. Entanglement, as the foundation of space-time, may sound abstract, but its consequences are vivid and concrete. Imagine tearing apart an entangled network. As the correlations weaken, the emergent geometry unravels. Distance becomes infinite, regions disconnect, and space itself fractures. Conversely, strengthen the entanglement, and the geometry becomes smooth and continuous. In this way, the shape of the universe is nothing more than the shape of entanglement. This perspective sheds light on the deepest paradoxes of black holes. Traditionally, a black hole seemed to consume information, erasing it behind an event horizon. Hawking radiation suggested that the whole would eventually evaporate, leaving no trace of what had fallen in. This violated the principle of quantum mechanics that information is never lost. But if space-time is entanglement, then the paradox takes a new form. The horizon is not a boundary of destruction, but a surface where information is encoded in correlations. As the black hole evaporates, the information does not vanish, but is slowly released through entangled radiation. The firewall paradox, the puzzle of whether horizons are smooth or violent, is likewise recast. If ER equals EPR, then Hawking radiation may remain entangled with the black hole interior through tiny wormholes, preserving information and smoothness simultaneously. Even the Big Bang, the ultimate singularity, can be reconsidered. In the entanglement picture, the singularity is not a physical edge of space-time, but a state of minimal correlations. The early universe was not a point of infinite density, but a configuration where entanglement had yet to spread. As quantum correlations grew, geometry expanded, creating the illusion of cosmic inflation. The arrow of time itself may arise from this spreading entanglement, as information becomes ever more distributed across the universe. What makes these ideas more than speculation is their testability. The holographic principle, the Ryuta-Kayanagi formula, and tensor networks provide precise mathematical frameworks that connect entanglement with geometry. Quantum simulators in the laboratory can mimic aspects of these relationships, offering glimpses into how space-time might emerge from entanglement. Experiments in quantum information are beginning to touch the frontier where geometry and entanglement meet. If these connections continue to hold, they will not only reshape gravity, but redefine reality. The conclusion is difficult to escape. Gravity is not fundamental. It is the manifestation of entanglement at large scales. Space-time is not a stage in which particles move, but the fabric woven by their correlations. The universe is a hologram, an entanglement network, a quantum code. Gravity is its geometry, emergent, illusory, but no less real for being an illusion. In the next chapter, we will confront the challenge of proof. Can these bold ideas be tested in observation and experiment? Can we decide whether gravity is truly emergent, or whether dark matter and energy are the right path after all? The search for proof will determine whether gravity stands among the fundamental forces, or whether it is revealed as the most familiar illusion in nature. The beauty of an idea, however compelling, is never enough in science. Theories must face the crucible of experiment and observation. Gravity, if it is emergent, must leave fingerprints that distinguish it from the picture of fundamental force carried by Newton's law and Einstein's relativity. The question is whether those fingerprints exist, and whether we have the eyes to see them. The search for proof has become one of the defining quests of modern physics, uniting the work of astronomers mapping galaxies with quantum physicists probing the strange behavior of entangled particles in the laboratory. The first arena of testing is the cosmos itself. For decades, astronomers have charted the motion of stars within galaxies. The pattern is always the same: stars far from the galactic center orbit, far too quickly compared to the pull expected from visible matter. According to Newtonian gravity, the speed should diminish with distance, like planets in the solar system. Instead, galactic rotation curves remain stubbornly flat. The traditional solution has been to posit dark matter, invisible particles that outweigh all the stars and gas. But if gravity is emergent, if it changes its behavior on large scales due to entropy or holographic effects, then perhaps there is no dark matter at all. Verlinde's entropic gravity offers precisely this possibility. Observations have put his idea to the test. Data from spiral galaxies show that his predictions align strikingly well with the observed rotation curves without invoking a hidden halo of dark matter. In some cases, the match is nearly exact. For supporters, this is tantalizing evidence that emergent gravity may be on the right track. But the cosmos is vast, and galaxies are only one piece of the puzzle. When astronomers turned their telescopes toward clusters of galaxies, a different story emerged. Here, the gravitational lensing maps the bending of light from background galaxies as it passes through the cluster did not line up with the visible matter alone. Dark matter explains the discrepancy neatly. Verlinde's framework, at least in its current form, struggles. The bullet cluster in particular remains a thorn, with its clear separation of visible matter and gravitational mass, suggesting that unseen matter really exists. Critics point to this as the death knell for emergent gravity. Advocates counter that the theory is still incomplete, that a fuller version may yet account for these observations. Cosmology provides another arena. The cosmic microwave background, the faint afterglow of the Big Bang, carries in its ripples a record of the early universe. The standard cosmological model, with dark matter included, reproduces those ripples with astonishing precision. Emergent gravity, so far, cannot. To match the microwave background, one must do more than reproduce galaxy rotation. One must explain the entire history of structure formation in the cosmos. This remains one of the greatest challenges for entropic and holographic gravity. Some see it as a fatal weakness. Others see it as a frontier, a place where the next breakthroughs must come if the theory is to survive. Yet it is not only the heavens that provide tests. In laboratories, physicists are beginning to probe the connection between entanglement and geometry. Quantum simulators made of cold atoms or superconducting circuits can mimic the behavior of entangled networks. In some of these systems, correlations create emergent notions of distance, much like in the tensor network models of holography. Though primitive, these experiments suggest that space-time-like behavior can indeed arise from quantum information. If such systems can be refined, they may allow us to watch space-time emerge in the laboratory, to see gravity itself as the byproduct of entanglement. Another avenue of testing comes from black holes. Gravitational wave observatories like LIGO and Virgo have opened a new window into their collisions. The detailed shapes of these waves, the way horizons form and merge, may carry subtle signs of whether gravity is fundamental or emergent. Already, physicists are looking for deviations from Einstein's predictions, hints that horizons are not smooth but statistical, that spacetime is not continuous but coded. The information paradox, once a purely theoretical puzzle, is now within observational reach. The search for proof is not only scientific but philosophical. If emergent gravity is correct, then dark matter may not exist, and decades of searches may have been misdirected. But if dark matter is found, if a particle is detected in a laboratory, if a signature appears in a collider, then emergent gravity may collapse as a primary explanation. The stakes are high, and the answers will reshape our understanding of the cosmos. In this tension lies the drama of modern physics, where bold ideas compete, not only in equations, but in the sky itself. It is worth remembering that proof in physics is rarely absolute. Theories are judged not by their beauty, but by their usefulness, their power to explain and predict. Newton's gravity was not wrong but incomplete. Einstein's relativity did not destroy Newton but expanded upon him. If emergent gravity succeeds, it may do the same, providing a deeper layer beneath Einstein's spacetime. If it fails, it will still have changed the conversation, reminding us that gravity need not be fundamental, that the universe may be richer than we imagined. And so the search continues. Telescopes scan the sky for the subtle bends of light and the motions of distant stars. Detectors lie deep, underground, waiting for a whisper of dark matter particles. Quantum laboratories cool atoms to near absolute zero, weaving entanglement into synthetic spacetime. Each path carries the possibility of revelation. Each experiment may tip the balance, deciding whether gravity is fundamental or emergent. Whatever the outcome, the quest itself reveals something profound. Gravity, the most familiar of forces, is also the most mysterious. It is the weight that keeps our feet on the ground, the engine that shapes the galaxies, the whisper of space-time geometry. And yet, it may be no force at all, only the shadow of information. In the next and final chapter, we will step back to reflect on what this means for our understanding of reality itself. If gravity is not fundamental, then the universe is not what it seems. Space and time themselves may be illusions, woven from quantum information, with reality lying in patterns deeper than geometry, deeper than matter, deeper even than space-time. Gravity began our journey as the most familiar of companions, the force we feel each moment of our lives, pulling us down, guiding the fall of rivers, anchoring the planets, sculpting the galaxies. For centuries, we thought we understood it. Newton gave us a precise law. Einstein gave us a profound vision of curvature. And physicists believed that in time gravity would join the other forces in the grand tapestry of the Standard Model. Yet the deeper we have pursued it, the more gravity has slipped through our grasp. At each turn, it has revealed itself not as a fundamental thread, but as a woven pattern, not as an indivisible law, but as an emergent phenomenon. We began by noticing that gravity does not fit with the other forces. Electromagnetism, the strong force, and the weak force can all be described within quantum field theory, mediated by particles, behaving in ways that match perfectly with the language of the Standard Model. Gravity resists. The graviton, the hypothetical quantum of gravitational interaction, has never been observed, and attempts to quantize gravity lead to infinities and inconsistencies. At the singularities of black holes and at the beginning of the universe, Einstein's equations break down. Gravity demands a different explanation. Jacobson pointed us toward thermodynamics, showing that Einstein's field equations emerge from the laws of heat and entropy. The holographic principle revealed that the maximum information in a region is stored not in its volume but on its surface, suggesting that space-time itself is a projection. Maldaceno's correspondence gave this principle mathematical teeth, showing that a gravitational universe can be equivalent to a boundary theory without gravity. Verlinde extended the vision, proposing that gravity is an entropic force, not a fundamental interaction, and that the phenomena we attribute to dark matter may instead be the signature of emergent gravity. Entanglement deepened the story still further, weaving space-time itself from networks of correlations, suggesting that wormholes and entanglement are two sides of the same coin. At each step, gravity retreated from fundamentality and revealed itself as emergence. What then are we to make of this? If gravity is not fundamental, then perhaps nothing we call fundamental is what it seems. Space and time themselves may be emergent. The smooth continuum we experience an illusion born of microscopic information. Matter and energy may be secondary, mere excitations within a deeper informational substrate. The true foundation may be quantum information, entanglement, and entropy. The universe may be a vast quantum code, with error correction written into the very fabric of space-time. This vision reshapes our philosophy of reality. For centuries, physics has sought smaller building blocks, reducing the world from molecules to atoms, from atoms to particles, from particles to quarks and leptons. But what if the reductionist path does not end with particles at all? What if the true building blocks are not things, but relationships, not matter, but correlations? What if the universe is not built from bricks of substance, but from the logic of information? In this view, gravity is the grand illusion that makes the code appear as geometry. It is the reason we believe we live in space and time, when in fact space and time are emergent properties of information flow. Gravity is the mask worn by entropy, the shadow cast by entanglement, the thermodynamic whisper of the universe's hidden microstates. It is the most familiar of forces precisely because it is the most universal, the residue of information at every scale. The implications are profound. If space-time is emergent, then the universe itself may not be infinite in the way we imagine, but finite in information. The horizons of black holes, the expansion of the cosmos, the arrow of time all may be explained as features of how information is stored, spread, and transformed. The fate of the universe may be not a heat death but an information equilibrium, where entanglement saturates and geometry ceases to evolve. Life, thought, and consciousness themselves may be patterns of information woven into the emergent fabric. And yet, for all its radical nature, this vision does not diminish gravity. To say it is emergent is not to say it is unreal. Temperature is emergent, yet it burns. Pressure is emergent, yet it can crush. Gravity, too, is emergent, yet it rules the cosmos. Its illusions have power because they are the way we experience the deeper truth. To recognize gravity as emergent is to deepen our respect for it, to see it not as a primitive force, but as the grandest consequence of the universe's hidden architecture. The search is not over. Observations will continue to test these ideas, and experiments will probe the connections between entanglement and space-time. Perhaps we will find dark matter particles after all, restoring gravity to its familiar place. Perhaps we will confirm that no such particles exist, and that gravity is indeed entropic and emergent. Either way, the pursuit itself enriches us. It teaches us that the universe is stranger than we imagine, that even the most familiar force may be an illusion, and that truth lies always deeper than appearances. So we end where we began, with gravity the familiar stranger, the pull that governs our days, and the curvature that shapes the stars. We have learned to doubt its fundamentality, to see it not as a basic law, but as an emergent phenomenon, not as a force, but as geometry, not as geometry, but as information. Perhaps the final revelation will be that gravity is not a thing at all, but the way the universe teaches us about its true foundation. If that is so, then to understand gravity is to glimpse the architecture of reality itself.